Our next topic is vapor pressure of liquid solutions. Now, liquid solutions can be of three types, as you know: liquid dissolved in liquid, as in toluene dissolved in benzene, then solid dissolved in liquid, like a sugar solution, then gas in liquid, like soda water. So, already we have seen gas in liquid type of solutions and Henry's law. Solid in liquid type of solutions will come to afterwards, and now we will consider vapor pressure of liquid in liquid type, and that is liquid solution. Now, vapor pressure, already you have studied about vapor pressure in class 11. So, considering a volatile liquid kept in a closed vessel, for example, if water or alcohol, we know the molecules will evaporate, will go to vapor state, and from the vapor state a few molecules will condense and come back to the liquid state, and a stage will be reached where rate of evaporation becomes equal to rate of condensation. And then if we measure the vapor pressure at this stage using a manometer, we will find the pressure remains constant, and this pressure exerted is called vapor pressure. So it is a pressure exerted by vapors in equilibrium with a liquid at a given temperature. And now considering liquid solutions where we have two volatile components. For example, component 1 and component 2. Now consider such a solution kept in a closed vessel. Since both are volatile, both will change to vapor state. Component 1 will go to vapor state and its molecules will be there in the vapor state. Component 2 also will go to vapor state. Its molecules will also be in the vapor state. Then molecules of component 1 in vapor state will exert pressure called partial pressure of component 1. Same way, molecules of component 2 in the vapor state will also exert pressure. That's partial pressure exerted by component 2. Let P1 be the partial pressure of component 1 and P2 the partial pressure exerted by component 2. Then let X1 be the mole fraction of component 1 in the solution and X2 the mole fraction of component 2 in the solution. Now the quantitative relationship between the mole fraction in the solution and partial vapor pressure is given by Rolle's law. Now Rolle's law, according to Rolle's law, the partial vapor pressure of each volatile component is directly proportional to mole fraction of the component in the solution. And therefore, in this case, we can write partial pressure of component 1, P1, is directly proportional to X1. Partial pressure of component 2, P2, is directly proportional to X2. And this again means that P1 is equal to a constant into mole fraction. And that constant is P10 or P1 naught, which is the partial pressure of, it's a vapor pressure of the pure component. When pure component is taken, component 1 alone is taken, we measure the partial pressure and that is P10. Same way, when component 2 alone is present, the vapor pressure measured is P20. So P2 is equal to P20 into X2, where P2 is the partial pressure of component 2, P20 is the vapor pressure of pure component 2, and X2 is the mole fraction of the component in the solution. This is Rolle's law. So once again, Rolle's law states that partial pressure of each volatile component is directly proportional to its mole fraction in the solution, and hence we have P1 equals P10 into X1, P2 equals P20 into X2. So total vapor pressure P total can be written as P1 plus P2. So substituting the value of P1 and P2 in this equation, we have P total is equal to P1 0 into x1 plus P2 0 into x2. But we know that x1 is equal to 1 minus x2. This we get from the relationship sum of mole fractions of these two components will be equal to 1. Therefore, we can substitute for x1 in this equation, and hence the equation becomes P total is equal to P1 0 into 1 minus x2 plus P2 0 into x2. Rearranging, we get this relationship, and that is P total. We can write this as P total is equal to P1 0 plus x2 into P2 0 minus P1 0. Now this is like P total y equals mx plus c, and this means that the total vapor pressure varies linearly with mole fraction of component 2 here. Of course, we can write it in terms of component 1 x1 also. And in this, we can represent this graphically. If you look at the graph, we find when we move in this direction, mole fraction of component 2 increases. And according to Rolle's law, partial vapor pressure of component 2 is directly proportional to its mole fraction in the solution, and that is P1 is directly proportional to x1. So we get a straight line passing through the origin. This is for component 2. Now component 2, here mole fraction is 0. As it increases and reaches the maximum value x2 equals 1, and therefore its vapor pressure varies linearly with its mole fraction, and hence we get a straight line passing through the origin. And this is P20 when component 2 alone is present, mole fraction is 1, and therefore this P20 is the vapor pressure of pure component 2. Same way, in the reverse direction, we know mole fraction of component 1 increases from 0 to 1. Therefore, its vapor pressure again varies linearly, and we get P10 when x1 is equal to 1. And total vapor pressure varies between P10 and P20. And since here x2, if you look at the relative values of P10 and P20, as far as this diagram is concerned, P10 is less than P20. This means that component 1 is less volatile than component 2, or component 2 has higher vapor pressure than component 1 at a given temperature, and therefore total vapor pressure we find here increases with increase in mole fraction of component 2. And if you consider the other way, we find the total vapor pressure decreases with increase in mole fraction of component 1. So if the component is more volatile, with increase in its mole fraction, the total vapor pressure will increase. So this is Rolle's law. So once again, Rolle's law states that partial vapor pressure of each volatile component is directly proportional to its mole fraction in the solution. And now if you look at this part, that is above the solution, the total vapor pressure, we find out using Dalton's law, because as per Dalton's law, the total pressure is the sum of the partial pressures, and that is why we write it as P total is equal to P1 plus P2. Now so we can use Dalton's law to find the composition in the vapor state, which you have already studied in 11th class. And for that, we consider here in the vapor state, let Y1 be the mole fraction of component 1 and Y2 be the mole fraction of component 2. This will be different from x1 and x2 in the solution, because more volatile component will easily vaporize and vapors will contain more volatile component. So Y1 and Y2 cannot be same as x1 and x2. So here we are considering Y1 and Y2 are the mole fractions of the components in the vapor state. Then according to Dalton's law, which you have already seen, this part, if you consider, this can be considered as the mixture of non-reacting gases. And therefore, applying Dalton's law, we can say P1 is equal to Y1 into P total, and P2 is equal to Y2 into P total. So this way we can find, and that is if we know P total, total vapor pressure, which we can measure by connecting this to a manometer, we can find out partial pressure P1 and P2 of the two components. If we know these two, we can find composition of these two components in the vapor state using this relationship based on Dalton's law, and that is P1 equals Y1 into P total and P2 is equal to Y2 into P total. And then if we consider again Rolle's law and Henry's law, if we compare these two, we find for a volatile component, as per Rolle's law, we know component P1 is equal to P10 into X1. And for Henry's law, according to Henry's law, partial vapor pressure P is equal to Kh into mole fraction of that gas, of course, in the solution. Now if you compare these two equations, you will find when P10 becomes equal to Kh, Rolle's law becomes a special case of Henry's law. So Rolle's law becomes a special case of Henry's law when P10 becomes equal to Kh, that is Henry's law constant. Then another important aspect or important part about this Rolle's law is, now if a solution like this obeys Rolle's law over the entire range of concentration, whatever be the range of concentration, if Rolle's law is obeyed, then such a solution is called an ideal solution. So an ideal solution is one which obeys Rolle's law over the entire range of concentration. For such a solution, the partial vapor pressure of component 1 will be directly proportional to its mole fraction in the solution, and partial vapor pressure of component 2 will be directly proportional to its mole fraction in the solution. So we say the ideal solution obeys Rolle's law. Now for obeying Rolle's law, when we mix the two components, there should not be any change in the intermolecular forces. And that is, the intermolecular forces formed between component 1 and 2 should be of the similar types present in pure components, that is between 1 and 1 and between 2 and 2. And considering this example of toluene benzene mixture, in toluene the intermolecular force present is van der Waals force, and in benzene again the intermolecular force present is van der Waals force. When we mix these two, the force between a benzene molecule and a toluene is again van der Waals force. So there is no change in the nature of the intermolecular forces. So we assume there is no change in the strength of the intermolecular forces on mixing, and that means there should not be any absorption of heat or evolution of heat. And also there should not be any change in the volume, in the sense if we mix 10 ml benzene with 10 ml toluene, we must exactly get 20 ml of the solution. It cannot be 20.01 ml or it cannot be 19.9 ml. In that case, we call that solution an ideal solution. So for ideal solution, the conditions, if we consider, it should obey Rolle's law over the entire range of concentration, and for such a solution delta H mixing must be 0, and that is there should not be any release of heat or absorption of heat, and delta V mixing must be 0, and that means there should not be increase in the volume or decrease in the volume, and that again means these conditions can be satisfied only if, and that is the intermolecular forces are similar, or this again means the interaction between component 1 and 1, component 2 and 2 should be similar to interactive forces between 1 and 2. That is, on mixing, the forces formed between 1 and 2 should be of the same type as existing in pure component between 1 and 1 and between 2 and 2. Then such a solution is called an ideal solution. At the same time, all the solutions, it's very difficult to get ideal solutions, but a solution like toluene benzene mixture is considered as a near ideal solution. And that means we have non-ideal solutions which will not obey Rolle's law over the entire range of concentration. So next we have to consider non-ideal solutions.